Assalamualaikum and hi everyone. My name is Muhammad Hakim JAAFAR. Entry number F2A1501. Today I will be presenting my web page called Advanced Precision Livestock Calculus, a bioeconomic livestock simulator. This project combines concepts from bioscience, calculus, and economics to study livestock. The web page is designed as an interactive simulator that helps users understand how cattle grow over time and how different economic factors can affect profitability. Next is the bioscience problem I chose is livestock growth, management and optimization. In livestock farming, it is important to understand how animals grow because growth directly affects production efficiency and profit. Animals do not gain weight at a constant rate throughout their life. Instead, they experience periods of rapid growth followed by slower growth as they approach maturity. Because of this, farmers need tools to predict growth pattern and make informed decisions about feeding strategies and production planning. My web page used a mathematical growth model to simulate cattle growth over time and shows how biological growth can be linked to economic outcomes. Studying livestock growth is important for several reasons. First, livestock production plays a major protein. First, livestock production plays a major role in providing food and protein for the world's population. Second, feed is the one of the largest costs in livestock farming. Understanding growth patterns help farmers use feed more efficiently and reduce unnecessary expenses. Third, better growth management can improve farm profitability by helping farmers identify the most productive stages of animal growth. Finally, improving efficiency can also contribute to more sustainable farming practices by reducing waste and maximizing resource utilization. For these reasons, livestock growth analysis is an important topic in bioscience and agricultural research. Okay, so now I will explain the main features of my webpage. First of all, we have bioeconomic market controls. First, we have the bioeconomic market control section. Here, users can adjust the feed concentrate price and the market beef price. This control represents real-world market conditions. By changing these values, users can observe how fluctuation in feed cost and beef prices influence the profitability of livestock production. This helps demonstrate the relationship between biological growth and economic decision making. Okay, next we have here is growth model. This graph shows how cattle weight change over time. At the beginning, growth is relatively slow. Then the animal enters a period of rapid growth before gradually slowing down as it approaches maturity. This pattern reflects realistic biological growth observed in livestock. The model allows users to visualize how weight develops throughout the animal life cycle. As you can see here, this graph shows a growth of a cow that breed named KK cattle, and this one is as you can see has the three model, which is the Brahman cross and Frisian Taiwan. Okay, so next I will explain about the first directive growth rate. So the first The derivative represents the animal growth rate, also known as average daily gain. This value tells us how much weight the animals gain each day. A higher growth rate means the animal is growing more efficiently. Farmers can use this information to identify periods when feed conversion is most effective and when growth performance is at its peak. The second one, we have a second derivative, which is growth acceleration. The second derivative measures how the growth rate changes over time. This helps identify the inflection point, which is the stage where the animal reaches its maximum growth rate. After this point, the animal continues to gain weight, but the speed of growth gradually decreases. Understanding this stage is important because it can influence feeding and management decisions. So the third part is interactive graph and simulator. One of the key features of the webpage is the interactive simulator. Users can click on different points of the graph to view detailed information for specific days. The simulator displays data such as animal weight, growth rate, growth acceleration, feed cost, and meat value. This interactive feature makes, makes it easier to understand how biological and economic factors change throughout the growth process. The, Finally, the economic analysis. The final section focuses on economic analysis. The simulator estimates daily feed, cost, and the value generated from livestock growth. Users can compare this value to better understand the relationship between production expenses and potential returns. This section demonstrates how mathematical models can be used to support economic decision making in livestock farming. Uh, One improvement I would recommend is adding comparison features to this HTML. This feature will allow users to compare different cattle breeds or feeding strategies at the same time. By comparing multiple scenarios side by side, users could better understand how different biological and economic factors affect livestock performance and profitability. In conclusion, this webpage demonstrates how bioscience, calculus, and economics can be integrated to analyze livestock growth and profitability. The simulator helps users understand growth patterns, growth rates, production costs, and economic returns through an interactive and educational platform. Overall, this project shows how mathematical models can be applied to solve real-world problems in animal science and agriculture. Thank you for listening.
Hello, my name is Ahmad SUFYAN binti Osman. My metric number is F25A1637. I'm from SFA. Today, I would allow to about to present to you is my bioscience problem, which is agroderivative, which is yield curve analysis and interactive tangents. A summary of the chosen bioscience problem. This bioscience problem, which is the core bioscience problem, focus on the decline in productivity and increasing operational difficulties of aging oil palm, which is Elasis genesis plantation in Malaysia. While all palm trees begin commercial production around year 3, they eventually hit a peak and experience a natural decline in fresh fruit bunch yields due to tree aging, canopy saturation, and biological senescence. Additionally, as the tree grows past 15 to 18 years, they can exceed heights of 12 meters, making manual harvesting highly challenging, hazardous, and economically inefficient. The biological problem is predicting this exact point of diminishing returns to plan timely intervention. The importance of studying this bioscience problem is the first is economic stability. Oil palm cultivation covers over 5.8 million hectares in Malaysia. Optimizing production directly safeguards a pillar of the national agricultural economy. Second is proactive research allocation. By determining the precise window when tree productivity slows down or drops drastically, plantation management can accurately budget and schedule massive replanting programs rather than reacting after a sharp drop in crop yield. The third one is harvesting safety and efficiency. Identifying when trees reach unmanageable physical heights allow agronomists to replace old crops with shorter, higher yielding variation, ensuring worker safety and lower labor costs. As you can see, this is an example of the mathematical models that we use here to make this graph. Here is the point is the takes all palm age to grow 12 years to increase uh, to plant a fresh fruit bunch in in a 20 years. It takes 19.39 year a year. And then ways to improve the HTML, which is to make the website easier for everyone to understand. The best improvement is to add an invincible safety net text description to complex match equation. Right now, the websites use a special coding language to display formulas, which can easily glitch on older smartphones, break on slow internet connections, or fail entirely for visually impaired students using screen reading software. By adding a simple plain text description directly into the background structure of the HTML, you create you create a backup system. If the fancy Mac graphics fail to load or a screen reader scans the page, the website will simply read out the equation in plain English, such as yield equals negative 0.004 times h cubed. This small adjustment ensures the agricultural simulator is universally accessible, completely mobile friendly, and reliable for every student regardless of their device or learning needs. The conclusion is that this e-agro derive project successfully demonstrate how mathematical modeling, especially calculus-based derivative analysis, can solve a critical real-world bioscience challenge in oil palm plantation management by analyzing the life cycle of a genesis through the age, yield rate, and marginal rate of change. The study provides a precise data-driven approach to tracking biological decline. Instead of relying on guesswork, plantation managers can use these mathematical metrics to pin down the exact inflection point where tree aging and canopy saturation cause yields to plummet and harvesting heights to become hazardous. Ultimately, studying these problems bridge the gap between pure plant biology and agricultural economics by proactively determining the optimal window for replanting. The industry can minimal waste, protect worker safety, and ensure the long-term economic sustainability of one of Malaysia's most vital crop sectors. Improving the accessibility and responsive of the HTML platform will further ensure that these vital agro-technical insights can be easily used by students, researchers, and farmers alike. That's all from me. Thank you.
Hi, my name is Abdul Wafiy bin Zulkifli. My metric number is F25A2065. Uh, Today, I will present a bioscience related calculus in Malaysia animal husbandry Kedah Kelantan cattle growth models. This website demonstrates how mathematics, particularly calculus, can be used to analyze cattle growth and improve livestock management. The bioscience problem is discussed in this website is the growth patterns of Kedah Kelantan cattle, which is a local breed in Malaysia. Farmer need to know when cattle growth most efficient, so they can provide the right amount of feed and manage production costs. The website use a logistic growth model to predict cattle weight over time and applies derivative from calculus to calculate the absolute growth rate. This helps determine the age at which cattle experience their fastest growth. Importance of studying this bioscience problem. Studying this problem is important because feed costs account for more than 70% of livestock production expense. By understanding the growth pattern of cattle, farmer can identify the most efficient feeding period. This improves productivity, reduce waste, lower costs, and increase profit. It also supports sustainable livestock farming and helps ensure a stable food supply. In this graph, Kedah Kelantan cattle dynamic growth kinetics. In yearly first moon, which is 0 to 10 moons, the graph show growth rate, growth velocity 6.15 kilogram in that moon. Total weight which is 38.4 kilogram. Next, moon 11 to 23 moons, the graph show growth velocity 15.52 kilogram. And total weight is 196.4 kilograms. This is the highest in that month. And next, 24 months to 30 months, the graph showing the decrease, which is growth velocity decreased to 9.36 kilogram, and the total weight keep gaining, which is 286.4, and that's I think I would recommend one way to make this HTML better, which is adding a result summary panel beside the graph. The panel could automatically display important information such as peak growth age, maximum growth rate, current cattle weights, recommended feeding periods. This would make the website easier for farmer and students to understand without needing to interpret the graph themselves. In conclusion, this website demonstrates how calculus can be applied in bioscience to study cattle growth. By using derivative to calculate growth rates, farmer can identify the most efficient period for feeding and livestock management. This helps reduce costs, improve productivity, and support sustainable agriculture. Overall, this project is a good example of how mathematics and biology can work together to solve real-world problems. That's all from me.
Hello everyone, my name is SYAZWANI binti Muhammad ZAINI. My nomenclature F35B1876. I would like to present my interactive HTML project titled Optimizing Kedah Kelantan KK Cattle Weight Trend via Derivative. This project combined bioscience and mathematics, especially calculus, to study cattle growth pattern and determine the peak growth rate of Kedah cattle. Okay, summary of the chosen bioscience problem. This project focused on the growth performance of Kedah KK cattle, which is a local Malaysian beef cattle breed. The bioscience problem here is how farmer can accurately monitor cattle weight gain and identify the best period for feeding management and marketing. Normally, farmers only observe the total body weight of the cattle. However, this project used the concept of derivative in calculus to calculate the rate of weight gain per day, also known as growth velocity. By using this mathematical approach, we can identify the exact time when the animal reaches its maximum growth rate. Okay. This project is important because KK cattle are available in Malaysia due to their heat tolerance and disease resistance. Understanding their growth pattern help farmers such as like improve the feed efficiency, reduce production costs, predict the best yield time, and improve overall farm management. Besides that, this project also shows how mathematics and bioscience can work together in agriculture technology. Using derivatives alone more accurate analysis instead of relying only on observation. Okay. Last section, the bioscience scenario. The section explains the real-life farming problem. Instead, the farmer need to monitor the average daily energy of cattle. The first directive writing us this is used to calculate the rate of weight gain per day. This helps farmer how know when the cattle growth start slowing down, so they can adjust feeding strategies or prepare for marketing. Okay, mathematics modeling. This section explains that the cattle growth follow assignment or S-shaped pattern. The graph is modeling using a cubic polynomial equation to present cattle growth over the time from the 0 until 365 day. Okay, this graph is the main part of the HTML project. The green line represents the cattle weight, while the yellow dot line represents the growth velocity or derivative value. Okay, the green line, the green curve shows that the cattle will increase over time. At the beginning, growth is slow, then become faster, and finally slow down again near maturity. And yellow dot line, the yellow dot curve shows that instantaneous growth rate. When the curve reaches its highest point, it means that cattle is growing at its maximum speed. Example point on the graph. Example like the 18 cattle weight is around 135.31 kilogram and the growth velocity is 0.457 kilogram per day. This means the cattle gain approximately 0.457 kilogram per day at that time. Okay. Rapid growth cycle in this button allows a user to replay the animation and observe the growth process again interactively. It makes the HTML more engaging and easier to understand. One recommendation to improve this HTML project is to add real-time data input and comparison between multiple cattle breeds. For example, users could compare cattle with Brahman or Angus cattle. This will make the system more interactive, educational, and useful for livestock raisers. So, in conclusion, this project successfully combined bioscience, agriculture, and calculus to analyze cattle growth performance. The use of derivative help determine the exact growth rate and provide useful information for livestock management. Overall, this interactive ML project is a good example of how technology and mathematics can support modern animal husbandry practice. Thank you.